7 is what I would call the prototypical problem in this part of Module 1. In other words, if you can feel your way through this problem, then you are exactly where you need to be in Module 1 right now. And it asks us to evaluate this expression, which has a bunch of fraction arithmetic going on. How do we do it? Where do we begin? Exponent first, according to the order of operations. Parentheses, exponents, multiplication and division, addition and subtraction. Let me ask real quick, before we move on to the exponents, let me ask about the parentheses in this problem. What are they doing? Yeah.
It's like singling out the 1/3 to make it its own, like you just said, like, so for the exponent you would do the whole number, the whole fraction as opposed to just the top.
Right. It's giving us a visual grouping together of that fraction 1/3 and telling us that what's happening to the 1 is also happening to the 3 is kind of another way to think about it, right? So that's all, which means there's not really anything for us to do with those parentheses other than to kind of understand the function that they're serving in this notation. So we're not going to do anything with it. We're just going to move on and think about the exponent. So the exponent here is 2. How do we evaluate that second power? 1/3 times 1/3. Let me ask another follow-up question to that. How come that 7/8 that's out in the front is not getting multiplied by itself? There's no parentheses or exponents around it. In fact, there's a missing symbol in between 7/8 and 1/3. What arithmetic symbol could I put there? Multiplication. And according to the order of operations, we're not going to even touch that multiplication until after we're done with the exponent work. So the exponent work that we'll focus on first is the 1/3 squared, or 1/3 times 1/3. What is 1/3 times 1/3? Straight across the numerator, straight across the denominator, 1/9. Okay, so we end up with 1/9 as the result of simplifying 1/3 the quantity squared. So then I'll put the rest of everything back in. We had 7/9 plus 7/8 times 1/9. And now our exponent work is done. So where do we go next? Multiplication and division. Whatever multiplication and division exists, we're going to do it proceeding from left to right. So I have one multiplication to do. Where is it? 7/8 times 1/9. And how do you multiply those two fractions? Straight across. 7 times 1 and 8 times 9. So I'm going to get 7 over 8 times 9, 72. And now when we look through our expression, there is no more multiplication or division to be had. So how do we finish? Now we have to do the addition, which of course is the hardest part in this problem, probably. What do we need to do in order to accomplish this addition of two fractions? All right, what's a good choice of a common denominator here? Yeah, 72 is the smallest choice that we can make. We could, again, have followed the just multiply the denominators together protocol. I might not recommend it in this case because we're going to get some pretty large number. What is 9 times 72? 648? Ugh. And then you would have to balance these fractions on a denominator of 648. I'm going to choose not to do that this time. And I agree with all of you. 72 is a number which 9 goes into and 72 also goes into. It's actually the smallest such. But then comes the task of actually balancing the numerators in these fractions. Let's look at the second fraction first. 7 over 72 becomes how many 72nds?
1.
Yeah, because I multiplied by 1. I didn't have to do anything to that second fraction. Again, just like the example we saw before, the larger of the two denominators just happened to be a common denominator for us. So it's only the first fraction that we have to do something to. What do I have to multiply by in order to turn 7/9 into a fraction with 72 as its denominator? 8. So what does the numerator turn into? 56. Great. That's definitely, in my opinion, the trickiest step in this whole problem is balancing those common denominators. Because now that they're balanced, how do we add these two fractions? straight across using the same denominator. Right, so we'll add straight across the numerator. We'll keep the denominator, 56 plus 7. Okay, and how do we finish? 72 on the bottom, 63 on top. Simplify. Is there an opportunity to simplify here?
Yes.
How do you know?
Because they're both divisible by 9.
They're both divisible by 9. Now, if you're unsure about that, you could always go through the process of completely finding all the prime factors of these numbers using a factor tree. If we were really going to be brutal about it, I might divide 63 by 3, make it into 3 times 21. 21 is then 3 times 7. That's as far as we can go. 3, 7, and 3. So there are all the prime factors of 63. 72, likewise, we can divide into 2 times 36. 36 is in turn 2 times 18. 18 is 2 times 9. 9 is 3 times 3. So we could go through all of this nasty work to find the complete factor tree of each of these numbers. And then just go looking for matched up pairs. So I have a pair of 3s I can match up, and then I have another pair of 3s that I can match up. But after that, we have no other things in common, right? We have a leftover 7 up here on the top, and we have 2 times 2 times 2 left over on the bottom. But all the common factors can be canceled. So I can divide by 3 on top and bottom and get rid of a factor of 3. I can divide by 3 again on the top and bottom and get rid of another 3. And what's left over at the end of that process? 7/8. I left over 7 from on the top, and 2 times 2 times 2, I left over 8 on the bottom. Perhaps a little unconventional way to reduce a fraction, but this is kind of, it's a recipe that if you follow it, you'll always end up canceling as much as you can cancel, and it'll show you the leftovers right there in your factorization.